And let's take a look at some problems out of 5.4. These are similar to some of the homework problems. So let's take this one and let's find the derivative. So the derivative of e to the x is e to the x, or generically the derivative of e to the u is e to the u times the derivative of the exponent. So if it's just e to the x and that's dx, it's just e to the x. If that's a function, it's e to the power times the derivative of the inside function, so u prime. So on this one, notice we have a product. So to take the derivative, we have to use the product rule. So if we call that u and that v, it's the derivative of the first times the second plus the first times the derivative of the second. The derivative of e to the x is e to the x. So that takes care of that term. And then 9 times the derivative of e to the x, which is e to the x. So if we wanted to, we could factor an e to the x out. Every term has an e to the x, so if we factor an e to the x out here, we're left with 1, we're left with an x, we're left with 9. So e to the x times 10 plus x is our derivative. If we look at the next one, again, the derivative of e to a power is e to that power times the derivative of the exponent. So y prime would be e to the u times the derivative of the exponent. So that's just a power rule. Bring the 2 down, x to the 1 less power. So our derivative is 6x e to the 3x squared. So again, the derivative of e to the u is e to the u times u prime. Here we have a quotient. So we could do this with a quotient rule, or we could rewrite this and call this 14 times e to the x plus x. And if we move that to the numerator, we have to put it to the negative 1 power. So since the numerator is just a coefficient, a constant, then we could use the chain rule here and not use the quotient rule. So 14 is a constant, it stays there. The derivative of this chain rule, so bring the negative 1 down. Do the parentheses to the 1 less power times the derivative of the inside. So the derivative of the inside, the derivative of e to the x is e to the x. The derivative of x is 1. So if we simplify this, these things are on top. This one is on bottom. So on top we have negative 14 e to the x plus 1. And if we move this to the denominator, because of that negative exponent, we have e to the x plus x squared. Excuse me, we have a common factor here, so we could cancel that out with one of those and just call that negative 14 over e to the x plus x. I'm sorry, those are not alike, are they? So let's go back. That's a 1, that's an x, those are not alike, so we can't cancel those out. So we stop here. All right, this one we want to find the second derivative. So since we have a radical, let's begin by rewriting that as x to the 1/3. So to get a second derivative, we have to have the first derivative. So the first derivative, to take the derivative here, we bring our exponent down. 1 less power, so if we subtract 1, we would get negative 2/3. And then to take the derivative here, that's the product rule. So the derivative of e to the 2x is e to the 2x times the derivative of 2x. The derivative of 2x is 2. So if this is u and that's v, this is u prime, do that times v. plus u times v prime. The derivative of natural log x is x on bottom, the derivative of x on top, so 1 over x. So we can rewrite this a little bit. Let's just call this 1/3 x to the negative 2/3 plus 2 e to the 2x natural log x plus e to the 2x over x. So now if we want our second derivative, we bring our negative 2/3 down. So we have a 1/3 already. Bring the negative 2/3 down. X to the 1 less power. If we subtract 1 from that, we would have negative 5/3. And then to take the derivative of this, we would have to use the product rule again. So the derivative of the first factor, e to the 2x, is 2e to the 2x times the derivative of the exponent. So we have another 2. So that's u prime times v. So u prime v. Now we take u times v prime. The derivative of this is 1 over x. And then we do the derivative of this one. So the derivative of that, we have to use the quotient rule. So if we call that u and that v, it's the derivative of the top. So the derivative of e to the 2x is e to the 2x times 2, the derivative of that, minus, so that's u prime, so times the denominator, minus the top times the derivative of the denominator over the denominator squared. So u prime v minus u v prime. U prime v minus u v prime, where these are u and v. So then we just need to simplify that as best we can. So our second derivative, we had negative 4 over 9. We can move this to the denominator and call that x to the 5/3. 2 times 2 is 4, so 4 e to the 2x times natural log plus 2 e to the 2x over x. On top here, we could factor out an e to the 2x, and we'd be left with a 2x minus 1, and that's over x squared. So we could leave it like that. We could get a common denominator, a couple of different things we could do there. But if you get to that point, I would be okay with that. All right, this one asks for maximums, minimums, and inflection points. So let's recall that for maximums and minimums, that's when our first derivative is 0. If we have an inflection point, that will be where our second derivative is 0. So I'm going to simplify this function first. We can divide each term by 2. So 8 divided by 2 will make that 4 e to the x. 8 divided by 2 will make that 4 e to the negative x. So if we take our first derivative, we would have 4 times the derivative of e to the x is e to the x. And then the derivative of the next term is e to the negative x times the derivative of negative x. The derivative of negative x would be negative 1. So our first derivative is 4 e to the x minus 4 e to the negative x. So we'll get our second derivative in a minute. But if we want to find our critical points, set that equal to 0. We can call that, we can write it that way. We can get rid of our fraction by multiplying both sides by e to the x. So if we multiply this side by e to the x, we get 0. If we do the first term times e to the x, we would have 4 e to the x times e to the x. And remember, when we multiply like bases, we add exponents. So x plus x will make that 2x. When we multiply that times this one, that e to the x and that one cancel. Okay, we can add 4 to both sides. Divide both sides by 4. And since our variable is in the exponent, take the natural log of both sides. So natural log of 1 is 0. Natural log and e cancel. If we divide by 2, we get x is 0. So that's our only critical point, x equals 0. Now we could do the first derivative test to find out if that's a max or a minimum, or we could use our second derivative test. So if we take the second derivative, the derivative of the first term is 4. The derivative of e to the x is e to the x minus 4 times the derivative of e to the x, negative x is e to the negative x times the derivative of negative x, which is negative 1. So our second derivative, 4 e to the x plus 4 e to the negative x. So if we substitute a 0 into our second derivative, we get e to the 0, which is 1, so we get 4. Put a 0 in here, so e to the 0 is 1. That's positive, which means we're concave up. If we're concave up at a critical point, that means that's the minimum. That's the only critical point that we have, so there's no maximum. We just have that minimum. If we need to know the y value, we would just plug that back in the original function. Now, if we look for possible inflection points, we set our second derivative equal to 0. So we have 4 e to the x plus 4 e to the negative x equals 0. Or we could, as we did last time, we could put this over e to the x and then multiply everything by e to the x. So that gives us 0. That gives us 4 e to the 2x plus 4. If we subtract 4 from both sides, divide by 4, and take natural log of both sides, those cancel, but here we can't take the natural log of negative 1. That's undefined. So there is no solution to that equation. There's no time when our second derivative equals 0. So this means our second derivative does not equal 0, which means no inflection point. We only have inflection points when this happens. If it never happens, then there's no inflection point. So we have no maximum, we have no inflection points, we just have a minimum when x is 0. So that's several problems with derivatives of e to the u. Now, let's look at some integrals. So if the derivative of e to the u is e to the u times u prime, then if we integrate both sides, then the integral of e to the u du is just e to the u plus c. So if we can rewrite our integral as e to a power times the derivative of that power, then that just integrates into e to the power. Now, every time we have an e, that doesn't mean it's going to fit this formula. Sometimes it does, sometimes it fits a different formula. But one thing we try is when we have e and an exponent is we try to see what would happen if that exponent were our u. So in this case, let's see what would happen if u were to be x cubed. That would make du 3x squared dx. Well, we're really close to that. We have x squared dx. We just need to pick up a 3, and then that would be du. If If we multiply by 3 on the inside, we divide by 3 on the outside. So this is e to the u. That's du. That integrates into e to the u. So that becomes 1/3 e to the u plus c, where u is x cubed. All right, if we take a look at this one, let's see what happens if we let the exponent be u. Then du would be 5 dx. So no variable, just a constant times dx. Well, that's good because we don't have a variable. So we can make this fit if we multiply by 5 here and divide by 5 here. That would make this e to the u, and that would make this du. So we would have 1/5. The integral of e to the u du is e to the u, and our u is 5x minus 9. So if we can make it e to the u du, then we can integrate it. If we let u be the exponent here, 1 over x could be called x to the negative 1. That makes it so that we don't have to take the quotient rule here. So du would be negative 1 x to the 1 less power dx, or negative, that's not 1 less than negative 1. 1 less than that would be negative 2, so that'd be negative 1 over x squared dx. So we have a dx, we have an x squared on bottom, we just need a negative 1. So we could rearrange this if we wanted to, don't have to. We could call it e to the 1 over x times 1 over x squared dx. If we think about this being a fraction, on top we have e times 1, which is e. On bottom, 1 times x squared, which is x squared on bottom, and then we have a dx. We need a negative 1, so we can put a negative there and negative there. Multiplying two negatives makes a positive. So we have e to the u, and then all of that is our du. So this is, again, the integral of e to the u du. So we have a minus out front. When we integrate that, we get e to the u plus c, where our u is 1 over x. So it's just rewriting it, picking the correct thing to be u so that we can make everything else du. This one is a little trickier because if we were to let u be the exponent of e, we would have a couple issues. Which exponent do we use? Do we use the 2x or the 5x? Well, if we use the 2x, du is 2 dx. So if we try to make this e to the u, everything else is not du. Du would need to be just 2 dx. Well, all of this stuff is not just 2 dx. So that creates a problem. So the same thing would happen if we pick this to be u. We would get a 5 dx. Well, that would be e to the u, but that is not 5 dx. But what we can do here is we can divide each term by e to the 5x. We can call this 9 over e to the 5x minus e to the 2x over e to the 5x. And we can just rewrite this. We can call the first one 9e to the negative 5x by moving that to the numerator. If we're dividing and our bases are the same, we subtract the exponent. And then we just integrate these separately. So we can integrate the first one with respect to x, integrate the second one with respect to x. So for the first one, let's pull a 9 out front. E to the negative 5x dx. And then for the second one, integrate e to the negative 3x dx. So for the first one, if this is u, du would be the derivative of that, which is negative 5 dx. So dx needs to be multiplied by negative 5. If we multiply by negative 5 here, we have to divide by negative 5 here. So this is e to the u, and that's du. E to the u du, which integrates into e to the u. Now, technically plus c, but since we have two different indefinite integrals, we'll put the plus c on the end. Okay, so for this one, if u is negative 3x, du would be the derivative of negative 3x dx. So dx needs to pick up a negative 3. So we need to pick up a negative 3 out front. Two negatives make a positive, so positive 1/3. The integral of e to the u du, which is e to the u, and then we can pick up our plus c. And then we can leave our answer like that.